Ever get that, like, uneasy feeling? When you're online, say you're buying something age-restricted, you have to prove you're old enough, right? But it's like, hold on, do they really need my whole birth date for this? Or think about all the AI stuff popping up everywhere these days. Images, text. How do we know it was actually made the way they claim? Like with the specific data and models, but without them spilling all their secrets. It's this weird balance. We want privacy, but we also need to be sure things are legit.
It's a real tension, isn't it? That need to keep things private, but also have ways to prove stuff. And that's exactly where this amazing innovation comes in. Zero-knowledge proofs.
Zero-knowledge proofs, ZKPs. It does sound kind of sci-fi, doesn't it? But it's a real thing. And it's getting so much attention because, well, it could change a lot about how we do things online.
Yeah, for sure. I mean, imagine a world where you could prove you are who you say you are without showing your ID card, passport, all that stuff. Or where online voting is totally secure, everyone knows the count's accurate, but your individual vote stays completely secret. That's the kind of crazy potential ZKPs have.
For our listeners who love getting into the nitty-gritty, who crave those aha moments, this is definitely one of those topics. Because ZKPs change how we think about proof itself. It's not about showing all your work. It's about proving you could show it without actually giving anything away. So for this deep dive, we've got a bunch of cool sources lined up, articles that break things down simply, real-world examples, even a research paper that goes deep into the whole ZKP landscape.
We want to give you the whole picture. What are these things? What makes them tick? What are the different flavors out there? And of course, most importantly, what can we actually do with them? All that without getting too bogged down in the super technical weeds.
Sounds good. All right, so zero knowledge. Just the phrase itself is kind of a mind bender. You're proving you know something, but you're not saying what you know.
Yeah, the whole idea of zero knowledge specifically refers to this cryptographic method, and it's important to not confuse it with zero trust, which you often hear about in cybersecurity. Zero trust is a security model based on the idea that you never automatically trust any user or device, no matter where they are.
Right, so that's more of an overall philosophy, a way of approaching security in general. Whereas zero knowledge is a very specific tool, a cryptographic method that lets you prove something without revealing the thing itself.
Okay, so how does this work in practice? We keep seeing terms like prover and verifier.
Exactly. So you always have these two players. The prover, who's trying to convince the verifier that something is true, and they want to do this without giving away any extra information. Just the fact that, yep, this statement is true.
This sounds incredibly abstract, though. Any way we can make this a bit more concrete, a bit more down to earth?
Oh, absolutely. The classic example, which tons of sources use, is the Alibaba cave analogy.
Okay, I'm intrigued. Let's hear it. Picture a cave, right? It's circular, and there's this secret door in the wall separating the two paths around the circle. To open the door, you need to know a magic word. Now, Peggy, she's our prover, claims she knows the magic word. To prove it to Victor, the verifier, without actually telling him the word, here's what they do. Peggy goes into the cave, picking either path A or path B. Victor waits outside. Then Victor shouts out either A or B, completely at random, and Peggy has to come out of that path.
So if she does know the magic word, she can just open the secret door and come out wherever Victor tells her to.
Right. But if she doesn't know the word, she's stuck on whatever path she shows at the beginning. So the only way she could always come out the right way is if she got lucky and Victor just happened to pick the same path she was already on. And the chances of that happening, just randomly, are 50-50.
So one time, yeah, she could just be lucky. But what if they do this multiple times?
There you go. That's the key. If they repeat this, say, 20 times, and Peggy always comes out the correct path, the odds of her just guessing right that many times in a row becomes super tiny, like practically impossible. So Victor can be really, really sure that Peggy must know the magic word. He doesn't know what the word is, but he's convinced she knows it.
That's a really cool way to illustrate it. And it shows how ZKPs often use probability. You don't get absolute certainty, but you get this extremely high level of confidence. Some of the stuff we read also mentioned another analogy, something about colored balls and a colorblind friend.
Oh yeah, that's another good one. It's about proving something is different without saying how it's different. So you have two balls, one red, one green, but otherwise identical. And your friend Victor, again, he's red-green colorblind. So to him, they both look the same, kind of grayish. You want to prove they're actually different colors, but without revealing which is which.
Okay, how do you do that?
Well, you give Victor both balls. He puts them behind his back, then brings one out to show you. Then he hides them again, mixes them up, and reveals one again. And he asks you, did I switch the balls or is this the same one as before? Since you can see the colors, you'll know if he swapped them or not. And if you get it right over and over, even though Victor can't see the difference himself, he becomes more and more sure that the balls must be different colors. He still doesn't know which one is red and which is green, but he knows they're not the same.
I like that. The really clever ways to explain this. So no matter what analogy we use, are there certain properties, like ground rules, that any zero-knowledge proof has to follow? I think the Wikipedia article we looked at mentioned three main ones: completeness, soundness, and then the zero-knowledge part itself.
Exactly. Those are the three big pillars. Completeness means if the thing you're trying to prove is actually true, an honest prover can always convince an honest verifier. Then there's soundness, meaning if the statement is false, no matter how sneaky a dishonest prover tries to be, they can't trick the verifier into thinking it's true. Well, except for a super, super tiny chance. Basically negligible. And lastly, the zero-knowledge part itself. The heart of it all, meaning the verifier only learns whether the statement is true or false, nothing more. No hints about why it's true, no extra information, no secrets revealed.
That article also got a bit more theoretical with a formal definition involving simulators. What's that all about?
It is getting into the weeds a bit there, but basically the simulator idea is a way to really lock down that zero-knowledge property. Imagine you have this hypothetical algorithm, the simulator. It can create a fake transcript of the whole interaction, the questions the verifier asks, the prover's responses, everything. But this simulator only knows the statement itself, not the prover's secret. If we can show that the simulator can create a fake conversation that's indistinguishable from the real one, then it means the verifier couldn't have learned anything from the real interaction that they couldn't have figured out on their own. No information leaked.
Okay, so even with a perfect fake conversation, nobody's the wiser. So we've got the concept, we've got the analogies, but how does this actually work? I mean, under the hood, it's got to be more than just Peggy and Victor shouting paths at each other.
You're right. Remember how in that cave example, Victor would challenge Peggy, like, come out of path A, and she could only do it consistently if she knew the magic word? Well, ZKPs in the real world work kind of like that, but with math and cryptography. The verifier gives the prover a challenge, a mathematical puzzle, and the prover has to solve it. But they can only solve it if they actually have that secret knowledge they claim to have. The more puzzles they solve correctly, the more confident the verifier becomes.
So instead of paths in a cave, it's like equations and algorithms.
Yeah, exactly. Those physical actions in the analogy become all these complex calculations happening behind the scenes. One way to think about it, as the Chainlink article pointed out, is with circuits. Not electrical circuits, but kind of a diagram of the computation broken down into steps, like logical gates and arithmetic operations. You have inputs going in, the circuit does its thing, and you get an output. ZKPs can prove things about how this circuit runs, like was the output correct given certain inputs without revealing what those inputs actually were?
And I think the research paper got even deeper into that, talking about how they represent these computations as arithmetic circuits, breaking everything down into super basic math, like addition and multiplication, but using this special system called a finite field.
That's right. Those finite fields provide the right kind of mathematical environment. They make sure that all the calculations behave in very predictable ways. And that's super important for cryptography, especially for building these ZKPs that are both secure and don't leak information.
Okay, so finite fields. It's like a mathematically secure playground for all these cryptographic games. Now, it's clear we don't just have one type of ZKP. We keep hearing about zk-SNARKs and zk-SNARKs. What's the difference?
You got it. zk-SNARKs. That stands for Succinct Non-Interactive Argument of Knowledge. Succinct, that means the proofs themselves are pretty small. Easy to send around, easy to check. Non-interactive means the prover just creates the proof once, sends it over, and the verifier can check it on their own, no back and forth needed. And as we said before, that argument of knowledge bit means the proof not only shows the statement is true, but also that the prover really does know the secret behind it.
Gotcha. Small proofs, simple verification, perfect for situations where resources are limited, like, say, on a blockchain. What about zk-SNARKs then? That's scalable, transparent argument of knowledge, right? So does scalable mean they handle bigger, more complex computations better?
Exactly. zk-SNARKs can handle much more complex stuff without the proofs becoming huge or taking forever to make. And that transparent part is also key. It means they don't need this trusted setup phase that some SNARKs do.
Hang on, what's a trusted setup? Sounds kind of not very trustworthy.
Well, with some SNARKs, you need this initial step where you create some secret parameters. can be tricky because if those parameters are ever compromised, it could potentially mess up the security of all the proofs created using them. SNARKs sidestepped that whole issue by using publicly verifiable randomness. And the Chainlink article pointed out that SNARKs also often require less back and forth between the prover and verifier, which can make them faster in some situations.
So SNARKs, smaller proofs, faster verification, but maybe need a trusted setup. SNARKs handle huge computations, no need for that setup, and potentially faster proving time.
Got it. Now, the research paper went pretty deep into the whole life cycle of a zk-SNARK, breaking it into stages. The front end, arithmetization, back end. Can we unpack that a bit? What's actually happening at each step?
Think of it like turning regular computer code into something a ZKP system can work with. It's a series of transformations, kind of like compiling code, where you start with something humans understand and turn it into something a computer can run.
Analogy game strong today. All right, so what happens in the front end then? That's where you start with the program, maybe something in a language like Python. The paper used a simple function as an example. You take that and translate it into something more mathematical, often an arithmetic circuit. Basically, you're breaking down the whole computation into these tiny steps, like additions and multiplications.
So that Python function, which seems simple to us, gets turned into this intricate web of basic arithmetic operations in this circuit thing.
Yeah. And those values flowing through the circuit, representing the variables, the results, they're treated as elements of a finite field. That's how we make sure the cryptography works securely, like we talked about before.
Right, the finite field, our math playground. So we've got this circuit now. What's next? Arithmetization. Sounds intimidating.
It's not as scary as it sounds. Basically, we take that circuit and turn it into a bunch of mathematical constraints. The paper focused on one method called rank 1 constraint systems, or R1CS. We basically encode the whole circuit as a system of linear equations. They're written in a very specific way, involving these matrices called A, B, and C, and a special vector called the witness.
Hold on, matrices, those tables and numbers. And what's this witness thing?
The witness is super important. It holds all the values computed in the circuit for specific input. The initial values, the intermediate results, and the final output. It's like a complete record of everything that happens during the calculation. The R1CS equations basically lay out the rules of the circuit. And if you have a valid witness, a set of values that make all those equations true, it proves the computation was done correctly.
Okay, so a valid witness means everything checks out. But we can't just show the witness directly, right? That would defeat the whole purpose of privacy.
Exactly. If someone saw the witness, they'd see all the secrets. So the next step is to turn all this stuff, the matrices, the witness, into a proof that hides the witness's values. That's where the back end of the SNARK lifecycle comes in. And yes, it involves polynomials.
Ah, polynomials, those things from algebra class, bring back memories. So how do we go from matrices to polynomials?
It's a clever trick that lets us create a much smaller proof. We take the R1CS, those equations, and transform them into something called a quadratic arithmetic program, or QAP. It's a shift from matrix equations to polynomial equations. The prover basically creates this special solution polynomial, often called AIX, that kind of represents a correct execution of the circuit. And this polynomial has to satisfy certain equations that involve another polynomial, zx, which the verifier already knows.
Okay, bear with me. We started with a function, went to a circuit, then matrix equations, and now we're at polynomials. I'm following. Kinda. How does this lead to a small, verifiable, and private proof?
Here's the magic. By transforming everything into this QAP, the prover can create this small piece of data, the proof, that basically says, hey, this HX polynomial exists, and it solves those QAP equations. Which means the original computation was done correctly. The verifier can check this quickly using a special equation without needing to see the whole computation or the witness. That's why it's succinct, tiny proof, huge computation.
And the zero-knowledge part, how do we keep the witness hidden through all this?
That's where we get into some seriously fancy cryptography, polynomial commitment schemes. These let the prover commit to their HX polynomial in a way that the verifier can check certain things about it, like its value at specific points, without learning the whole polynomial or any of the secret witness values. They're kind of like a way to interact with a hidden mathematical object. The paper really emphasized how important these are for making SNARK secure and achieving both small proof size and zero knowledge.
So it's like layers of mathematical abstraction, hiding the secrets deeper and deeper until you get this little proof that magically confirms everything without giving anything away. Now, the paper didn't stop there. It also talked about all the tools being built to make this stuff easier to use. Zero-knowledge virtual machines, ZKVMs, domain-specific languages, ZKASLs, libraries, frameworks, even hardware acceleration. Let's start with the zk-VMs. What's the idea there?
zk-VMs are all about making life easier for developers who want to use zk-keys. Traditionally, all this stuff was super complex. You had to be a cryptography expert to build those circuits, set everything up, manage all those computations. zk-VMs aim to take care of all that behind the scenes. They're like a virtual machine, basically. Software emulating a computer, but specifically designed to run programs and generate zk-keys for those programs, all while keeping everything private.
So instead of building a custom zk circuit for every single application, you take your program, run it in the zk-VM, and boom, you get a zk.
That's the goal. The paper showed a typical zk-VM architecture. You've got memory, an operating system, registers, a CPU, and this special backend for creating the proof. The developer takes their program, maybe written in C++ or Rust, compiles it to a format the zk-VM understands, does a little setup to hide the secret inputs, and then the zk-VM runs the program step by step. As it runs, it generates the proof, which someone else can then check to make sure everything was done correctly, all without seeing the actual code or data, of course.
Okay, so zk-VMs handle all that heavy lifting at a pretty high level. The paper mentioned RISC-0 and Midden as examples. What's special about those?
RISC-0 is cool because it lets you create zk-keys for basically any Rust or C++ code, which opens up tons of possibilities. And Midden is interesting because it automatically generates SNARK proofs. Both of them are trying to make using zk-keys much, much easier for everyday developers.
Makes sense. What about zk-DSLs then, those domain-specific languages the paper mentioned? How are those different?
zk-DSLs are a bit lower level than zk-VMs, but they still make things easier. It's like a programming language specifically designed to make creating zk circuits easier. You use the DSL's syntax and commands, and it handles the tricky part of turning that into an actual circuit, usually that R1CS we talked about before.
So it's like a programming language that speaks zk. It knows all the rules and constraints.
Exactly. The paper had a table comparing different zk-DSLs, and it also talked about some of the challenges they face, like how to manage memory efficiently, how to deal with things like if-else statements, and how to handle situations where variables can change their value, which can be tricky for zk circuits. There were some good examples, like Circum, used in projects like Tornado Cache, Lurk, a LISP-based language for zk-SNARKs, and Leo, specifically for blockchain applications.
Sounds like zk-DSLs give developers more control over the circuit creation, but maybe need a bit more expertise than using a full-blown zk-VM. Now, beyond all this, the paper talked a lot about libraries and frameworks. What do those do in the zk world?
They're like toolkits. They provide these pre-built components called gadgets that do common cryptographic operations within those zk circuits. Think of it like having a toolbox full of pre-made parts. Instead of building every single function from scratch, you can just grab a gadget from a library and plug it in. It saves tons of time and effort, and it means developers can focus on their specific application instead of reinventing the wheel.
So it's like a shortcut. Use a pre-made, tested component and save yourself a headache. What kind of things are in these libraries?
All sorts of stuff. Basic math, logical operations, range proofs, proving a number is within a certain range, hash functions. The paper even had tables listing different gadgets, proving systems like Groth16 and Planck, and even different types of elliptic curves that are commonly used. It also talked about some cool trends like the growing popularity of smaller finite fields for better efficiency and the need for special zkp-friendly versions of half algorithms and digital signatures. Some well-known libraries are ArcWorks, written in Rust, Snark in Go, Halo 2 used by Zcash, and others.
It's really amazing how this whole ecosystem is developing, making zkPs more and more practical. And finally, let's talk about hardware acceleration. Given how computationally heavy all this stuff can be, it seems pretty important, right?
Oh, absolutely. Generating those proofs, especially for big, complex programs or large data sets, can really push regular computers to their limits. Hardware acceleration is all about using specialized hardware like FPGAs, GPUs, ASICs to make those computations way faster. They're optimized for the specific types of math used in zkPs, like those multiscalar multiplications, MSMs, and number-theoretic transforms, NTTs.
So we're basically outsourcing those heavy math problems to these specialized chips that can crunch numbers much, much faster. And the paper even mentioned a few examples.
Yeah, like Icicle, using NVIDIA GPUs, Ingam developing their own ZPU, a zero-knowledge proof processing unit, and CISIC, focusing on ASICs specifically for zkVMs, plus others like Fabric Cryptography, Irreducible, Supranational. It's definitely a hot area.
It feels like hardware acceleration is essential if we want zkPs to really take off and be used for all sorts of applications. Okay, so we've covered the tech. Now let's get to the good stuff. What are people actually doing with all this? The paper gave us a whole breakdown of both blockchain and non-blockchain uses.
Right, and it's really incredible how broad this stuff is already. Starting with blockchains, we see ZKPs being used on the foundational level, like in Zcash. They use zk-SNARKs to hide the sender, receiver, and amount of every transaction, making them truly private, which is different from how Monero does it, by the way, using ring signatures and stuff. Then there's Aleo, focused on private smart contracts, and Mina Protocol, using those recursive zk-SNARKs to make the blockchain super scalable and keep the whole network size small.
Lots of privacy-focused stuff there. What about those layer 2 scaling solutions everyone's talking about, like ZK rollups?
ZKPs are essential for those. They're what make them work. The idea is you move the actual transaction processing off the main blockchain onto a separate layer, a layer 2. Then you generate a ZKP that proves all those transactions were done correctly. This proof goes back to the main blockchain, and because it's small and easy to check, it's much cheaper and faster than verifying everything directly on the main chain. So you get way more transactions per second, lower fees, the whole 9 yards. The paper mentions several big projects working on this. zk-Sync Era, Polygon, zk-EVM, Scroll, Linea, Starknet, Aztec Network. It's a really competitive space right now.
So ZKPs are basically enabling this new wave of blockchain tech that's both faster and more private. What else is happening in the blockchain space? The paper also mentioned interoperability, making different blockchains talk to each other, and then all that stuff about private smart contracts and even ZKP-based identity.
Right, those are huge areas too. For interoperability, you have projects like ZK Bridge and Telepathy. They're using ZKPs to verify stuff between different blockchains, which could make the whole ecosystem much more connected and flexible.
It's like building bridges between these separate blockchain worlds.
Exactly. And for making smart contracts and transactions more private, there's Tornado Cash, Privacy Pools, Penumbra, and Mina Zcaps. They're all about doing stuff on the blockchain without revealing all the details.
And then that whole identity thing, the idea of proving something about yourself without showing all your personal info, that's going to be huge.
It is. There are projects working on anonymous credentials, like ZPass on the Aleo blockchain. There's World ID, using biometrics for verification while keeping your identity private. And others like Semaphore and the Galex protocol. This could really change how we log into websites, prove our age, all that stuff, without giving up our privacy.
Wow, so many things happening in just the blockchain world alone. But it's not just blockchains, right? What about non-blockchain applications? I know the paper mentioned ZKPs for identity stuff early on, even before blockchains were a thing.
You're right. The basic idea of proving something about yourself without revealing your identity, that's super useful in all sorts of situations. And that's exactly what those early ZKP systems were exploring. Now we have more modern stuff like ZK Creds, which lets you create anonymous credentials from your existing ID documents. It's like having a digital ID that only reveals what's absolutely necessary.
And then there's that whole ZK for machine learning thing, ZKML. That sounds super cutting edge, like right at the intersection of two huge fields.
Oh, definitely is. ZKML is about bringing those zero-knowledge guarantees to the world of AI. Like, imagine verifying the results of a machine learning model without seeing the model itself or the data it was trained on. Or training a model on sensitive data without anyone, even the people doing the training, seeing that data directly. There are a bunch of projects working on this: vCNN, zk-CNN, zkDL, Kaizen, zk-LLM. They're figuring out how to apply ZKPs to things like image recognition, natural language processing, all that stuff.
It's crazy to think you could have AI doing all this analysis, but with strong privacy built in. The paper also mentioned some other cool non-blockchain stuff, like secure voting, image authentication, even a ZKP-based peer-to-peer network.
It just goes to show how wide-ranging this stuff is. ZKPs for secure voting could revolutionize elections. Photo proof, using ZKPs for image authentication, could help fight fake news and deepfakes. And then those verifiable delay functions, VDFs, which are like time locks, are useful for all sorts of applications where you need randomness and can't trust a central authority.
We could keep going all day. There's so much.
Yeah.
So where is all this headed? What does the future hold for ZKPs?
The paper had a section on that too, talking about trends and research directions. A big one is making snark-proof generation even faster and more efficient. There's also work on improving how different layer 2 roll-up solutions can work together. And then this fascinating idea of combining ZKPs with game theory to build things like private auctions and dark pools.
It feels like the possibilities are almost endless. So, to wrap things up, what are the key takeaways for our listeners? What should they be thinking about after this deep dive?
Well, first, the basic concept of ZKPs is pretty amazing. You can prove something is true without revealing any extra information. It's this incredible balancing act between privacy and verifiability, which is so important in our digital world.
We've got those two main families, SNARKs and STARKs, each with their strengths. We've seen how those SNARKs are built, going through all those transformations from regular code to those mind-bending polynomials. And then we've got all these tools being developed, making it easier for developers to build their own ZKP applications.
And then, of course, there's just this huge range of applications from blockchain privacy and scaling to secure AI and digital identity. It really is a technology that could touch almost every aspect of our lives.
Hopefully, this deep dive has given you a better understanding of this amazing technology. It really makes you rethink what it means to know something and to prove something.
As ZKPs continue to develop and become more widely used, it's worth thinking about the big picture. How might they change how we interact online? How might they affect how we manage our data and trust digital systems? Could they be the key to building those truly private and scalable applications we've been dreaming of?
These are big, important questions. And if there's one thing this deep dive has shown us, it's that the answers are still being written. We encourage you to dig deeper into the aspects that you found most interesting, whether it's the blockchain stuff, the AI stuff, or just the pure cryptography behind it all.
Thanks for joining us on this journey into the world of zero-knowledge proofs. It's a world that's full of incredible potential.